Good morning, Art.
Good morning. I'm fooling around.
This just started and I hadn't even launched it or anything, that it just opened up.
Okay. I'm just fooling around with it.
There you are.
Hmm.
How are you?
Oh, pretty good, pretty good. Let's see. I'm trying to play around with my background.
It's lovely.
There we go.
Oh,
How's that for a background for today?
that's fine. I tell you, that second chapter. First chapter, I kind of got the basic gist of it. But that second chapter, like,
I'll try
And I
to make some sense out of it for you.
well, and I know every discipline has their own language that means certain things.
Right.
And maybe, like, I remember looking up one word and it was he could have used a perfectly normal word in its place, but maybe it had a scientific nuance for the one he used. I don't know.
That's the problem. I
Yeah.
understand it entirely. So I'm going to try to interpret some of this for you. And
Okay.
my
Hi, Dave.
basic process is not to use any mathematics. Try to do it.
And don't use any $50 words.
Try to do everything with pictures.
Iris.
Hi.
Hi, Iris. It's so good to see you. I don't think she's connected to audio yet.
Yeah, not yet.
There she is. Hi.
Hi, how are you?
Fine. It's so good to see you.
I don't know. I didn't think my face would show up.
Well, we want to be able to see.
Yeah.
No. How can I stop
You
this?
do.
Art.
If you go down to the bottom left, there's a stop video if you need to just have your
Yeah,
name up there. Yeah.
there you go. All right,
Now
thank you.
Okay. Hey, Art, will you need me to do the screen share, or do you think you've got it?
Well, let me see now. I've never done this before. So there's a button here called share content.
There's should be a bottom green thing that says share screen on the bottom row.
Well, it's actually on the top. I'm on an iPad, not a laptop.
Oh, well,
So-
if you want, I can do the share screen and you can just say next and I'll go to the next slide if you want me to do that.
Okay. Yeah, it's asking me to get, a screen. Let me see, just a minute. Let me try that.
Helen, how are you doing?
I'm fine. How are you?
Good, good. We've got grandkids here. So if you hear little voices in the background, it's because they're out at the pool and I'm in the bedroom and it's kind of near the pool. They are so full of energy. So much fun. Yeah.
Oh, I know. How old are
Let's
they?
see, we've got Ethan is 5, Emery is 2, almost 3, and then Maddie is just 6 months old. Hi, Nancy.
Hi, good afternoon.
Hi,
I'm
Nancy.
gonna put myself on mute right now. My husband is watching TV and I hear it too easily.
Do you hear it? Yeah. It doesn't sound bad though. Got to say that. I was worried about it too. TV was on earlier and it sounded like it was just amplified coming down the hallway.
Dave, I think we're gonna have to do it, where you throw up the file and,
Yeah, that's easy. And you just say
Okay.
next and we'll go to the next slide.
yeah, because I mean, what I've got is, wait, there's some more. Yeah, what I've got is something that says share content.
You know, I
It's
don't
up at
even,
the top. I mean, so the iPad, of course, has a different program for Zoom than a laptop does.
Yeah.
And
I
it has
go
share content, and one is screen. But when I put the thing on the screen, that it doesn't really share it.
yeah. Yeah, it'll be easier doing it
Yeah,
my share.
okay, that's fine.
Cool. Okay, we'll wait just a couple more minutes and see who else joins us. Gloria, how you doing?
Good. How are you?
Great. Very excited about this day. I'm prepared to have my mind blown.
I think mine's already blown. But in a good way.
Yeah.
I loved reading about Big Bang Theory and the principle and all of that kind of stuff. I'm just kind of, I mean, I don't understand it all, but I'm interested.
Yeah, that's the first step. Yeah. Yeah, it's gonna be fun. Well, not fun in a roller coaster kind of way, but fun as in growing. Yeah.
Yeah.
Getting to see the universe through art's eyes.
Right. Right.
Well, let's see. It's 12:30, so I thought what we could do is check in, and I'm going to read part of Eucharistic Prayer C, the one that's often called the Star Trek or Star Wars,
Oh, yeah.
but it seems appropriate to today. And I do
Yeah.
love Eucharistic Prayer C, but very few people do. So this would be one of my few chances to read it. So for checking in, let's just any news from anybody this week? Any kind of, we do have some news on Bill Schenker. So he went in and had I think, well, he went in to have a quadruple bypass, but I don't know if he
Oh,
actually,
wow.
yeah, it's always, I haven't heard the results other than that he is doing very well. He's unhooked from all the machines and things that go into him. I think he's looking at like a 60-day recovery. So, yeah.
Had
So
no idea. I'm so sorry.
yeah, I don't know that it was that far in advance planned. So I don't, seemed like it came on him pretty quick. And hopefully we'll have Susan back here, Susan and Bill in the next few weeks. We can find out more of the details. Okay. And Helen, you're healing up pretty well.
Yes, I even wore heels to church this morning. I thought that was a big step.
Yeah, good. And so I missed church today and I wasn't even able to watch it on the Facebook. How many of you actually attended today?
I did.
Good. Okay, and Iris, you did too? Great.
Yeah.
Good. Did Becky preach on the Good Shepherd?
Yes. Very
Yes,
good. Very well
it was
done.
great.
Very
Great.
well done.
I'll have to-
A
I'll have
good
to-
shepherd sermon.
Yes, a Good Shepherd sermon. Good. I'll watch it later on. A friend of mine, a Lutheran chaplain, used to say that, Jesus is a good shepherd, and we're just a bunch of sheepdogs helping out. So we're proud to be a sheepdog. Maybe that's what the collar's for. Okay, well, I'm going to open us up with some prayer. It's from Eucharistic Prayer C, and then we're going to turn it over to Art, and we're going to go through chapters 1 and 2. This is really kind of designed so that people don't even have to read or understand what they're reading, because we'll be able to get a lot just from the presentation. And I've looked at the slides and they are amazing, Art, so thanks. So the Lord be with you.
And
Also with you.
You.
God of all power, ruler of the universe, you are worthy of glory and praise. Glory to you forever and ever. At your command, all things came to be. The vast expanse of interstellar space, galaxies, suns, the planets in their courses, and this fragile earth, our island home. By your will, they were created and have their being. From the primal elements, you brought forth the human race and blessed us with memory, reason, and skill. You made us the rulers of creation, but we turned against you and betrayed your trust, and we turned against one another. Have mercy, Lord, for we are sinners in your sight. Again and again, you called us to return. Through prophets and sages, you revealed your righteous law. And in the fullness of time, you sent your only Son, born of a woman, to fulfill your law, to open for us the way of freedom and peace. By his blood, he reconciled us. By his wounds, we are healed. Amen.
Amen.
Okay, Art, should I put share screen, or did you want to set it up first?
No, let's just jump right into it.
Okay, hold on just a sec. Got to close a few things out here. Okay, does everybody see my wife at this point?
Oh, yes.
yes.
Yeah, okay, so we're in the right,
Mhm.
in chapter 1.
All right. Okay, so here we have this universe that we were just thanking God for. And the point that Polkingham is making here is that this universe displays an evolving fruitfulness, as he calls it. Now, the universe, from a scientific point of view, is made up of particles held together by forces. So let's go to the next one. So I presume everyone has learned something about this somewhere, sometime in their education.
Long
But-
time ago.
Atoms, the universe is made up of atoms, which consist of a nucleus, which consists of neutrons and protons, and the nucleus is surrounded by electrons orbiting around them. The electrons have a negative charge, the protons in the nucleus has a positive charge, and so it's the electric field produced by the positive charged protons attracting the electrons that hold the electrons on the atom. But there's a lot more to it than just that. Next slide. So this is all of modern physics in a nutshell. Starting from the left, let's see. We have materials made out of lots and lots of molecules, and that can be biomaterials as well as simply physical materials, crystals and so forth. So molecules are made up of atoms that are attached together by special forces, and those are quantum forces too. The atom, as we've just said, is made up of a atomic nucleus in the center, which is the red and purple balls, circled by electrons. And then we have whoops, no, I'm trying to get rid of Gloria. She's in my way. There we go. Then the the protons and the electrons are made up of something else, which is now really starting to get strange, called quarks.
Hmm.
So quarks are just particles that can only be observed in high energy accelerator facilities. But by smashing mainly protons together, you can observe these other little particles that come out called quarks, and they have features that are the that are categorized in high energy nuclear physics. But the theory now is that even the quarks are made up of something called strings, which are very theoretical. The strings are incredibly small, but these vibrating strings are the fundamental particles underneath quarks.
Hmm.
And who knows if something else is beneath the strings.
Wow.
Next slide.
So Art, for the
Yeah.
for finding these parts, you mentioned the high speed. Is that like the thing in Switzerland or Austria or something?
Yes. Okay, Switzerland is CERN, CERN, and it's a huge accelerator that actually passes into France. No, yes, it's in Switzerland and actually passes, part of the accelerator loops through France. It's so big.
Wow.
I could say very much about those, but I won't right now.
Okay.
Another entity, but anyway, if anyone has any questions, as I'm going to try to get through this fairly rapidly so we can get back to Polkinghorne, but if anyone has any questions, go ahead and stop me and I'll try to answer them. Another physical entity that's very important is electromagnetic radiation in the form of photons. There's a great controversy as to whether photons were particles or waves, and the controversy was finally resolved by quantum mechanics, in which things can have both a particle-like properties and wave-like properties. But photons are oscillating electromagnetic fields, as illustrated in the little picture with the arrow, where the blue arrows are a oscillating electric field and the red arrows are an oscillating magnetic field. And these things oscillate in tandem as the photon moves through space. And all photons move through space at the speed of light. The properties of the photon are produced by their frequency. That is the wavelength of the photon. And the figure underneath shows the whole electromagnetic spectrum with wavelengths converted into frequency so that it going from the lowest frequencies on the left to the highest frequencies on the right. The visible spectrum is the little circus tent, which shows that red light has a lower frequency and purple light has a higher frequency. So we go from infrared at lower frequencies to ultraviolet at higher frequencies. And above that, you get into X-rays and gamma rays. Yet those are the photons. Any question there?
So many.
We'll go on then.
Okay.
Okay, there are four fundamental forces. As the universe is made up of forces and particles. There's high energy nuclear physics have picked out some very strange forces. There's a force that holds the atomic nuclei together. It's not an electromagnetic force, it's a separate force all of its own called the strong force. And it's what makes the neutrons and protons so permanent. There's another force called the weak force, which is responsible for breaking the strong force and causing radioactive decay. Then we talked about the electromagnetic force, magnetism, which is between positive and negative charge, and the magnetic force due to moving charged particles. And then there's gravity. Next, we'll talk about those forces a little bit more in just a second. Okay, so gravity was what really got physics started with Newton working out how gravity holds the moon in orbit around the earth and the earth in orbit around the sun. But it's basically a force between two masses. And it's worked out, well, they'd throw in an equation. The force of gravity it is greater as the masses get greater, and it decreases as the distance between the masses increases. And the gravitational constant is a constant of nature and is related back to the speed of light in a certain way. Okay, next slide. Then there's the electric forces. All forces are something that just pushes matter around, causes objects and particles to change their motion in some way. So I think electric forces are between positive and negative charges. If the charges are the same as on the left, it's a repulsive force that pushes particles apart. If the charges are different, positive and negative, it's an attractive force that pulls forces together. Next slide. Just to mention them. Now, even the forces are sort of particle-like in the deeper quantum electrodynamics. And it's visualized by a concept called a virtual particle. So virtual particles are created out of the vacuum in particle and antiparticle pairs when something interacts with something else. So this electric force, for example, if two electrons are traveling towards each other, these would be the two things saying electrons at the bottom. So space is right and left and time is up and down in that figure. So we got two electrons approaching each other. And when they get a certain distance apart, a virtual particle is produced in space by their mutual mutual perturbation or disturbance of the fourth dimensional space-time continuum, and a little photon-like particle is created, which pushes the electrons apart. It's created very fast, and it immediately disappears. And so this is an idea, but fundamental to high energy nuclear physics, high energy quantum electrodynamics. Next slide. So, as Polkinghorne explained, the universe as we know today emerged from this fiery singularity. Something happened in a space so small that it's called a singularity. It has virtually no dimension. It's so small. And whatever it was, it happened about 15 billion years ago. And it was a huge expansion. All of time and space, in fact, was in that point. And all the energy of the whole universe was in there. And so it immediately started expanding. The physics of something so compact and so hot is beyond ordinary physics. No one really understands what was happening in there, but it was expanding very quickly. Next slide. So it eventually expanded out into enough space so it could cool off a little bit, and it cooled off to the point that stars could begin to form out of gravitational attraction of the hydrogen and helium, which was all that was in the whole cosmos at that point. And the little boxes shows a sort of almost uniform distribution of hydrogen, helium. And then it began to clump a little bit around very, very tiny fluctuations in the density of this hydrogen and helium gas. And as gravity began to clump these things together, eventually enough hydrogen and helium fell into one another until they heated up and created a star. And so stars were born. Next slide. So inside the stars, the early proto-stars, it was the basically fission going on which is shown here from top to bottom. You see two hydrogen atoms labeled H1, which are red, collide with enough energy to fuse together into a molecule of hydrogen called H2. And a proton is lost. I'm sorry, a neutron is lost in the process. The H2 then collides with another H1 in the star, and that forms helium, another nuclear fusion, energetic fusion. And each of these collisions release energy, which keeps the star hot. And all of that happened very fast in the beginning of the universe. But this is where it gets interesting. The next generation of stars had a lot of hydrogen and helium in them. And so helium atoms collided and were able to form an atom of beryllium, have enough protons to be what we call today beryllium. Again, some energy was released. The beryllium then collided with some more of the helium-4 that was in the star. And those neutrons and protons, when you mix them up, become carbon-12. Now, this is an amazing thing. Let's say, I think it's on the next slide. It's a very important thing to this whole idea of that Polkinghorne is talking about. Ordinarily, even at lots of different, at most temperatures or interstellar temperatures, the hydrogen and helium, helium atoms wouldn't actually transform into beryllium. That can only happen at a certain temperature within the star. But at that certain temperature, the probability of producing the beryllium rapidly shoots up. It's called a resonance. A little bit above it, probability drops rapidly. A little bit below it, the probability is too low for it to actually happen very much. But at a certain temperature, this interaction is very probable. And it turns out then, at that same temperature, the probability of the beryllium interacting with a helium atom is also very high. And those two form carbon-12. But it turns out that those high probabilities, there's no real reason why those high probabilities should be there at those certain temperatures. They're just there. And if they weren't just there, and if stars weren't at the temperature that they were at that time, there would be no carbon-12, and there would be no carbon-based life in the universe. But it was. And these stars then eventually went through their stellar lives, blew up as supernova, and threw carbon-12 all over the universe. And along with a lot of other necessary atoms for life to be. So this just the fact that there was enough, there's lots of strange facts. For instance, at the beginning of the universe, there was equal numbers of particles and antiparticles. And when particles and antiparticles meet, they convert back into pure energy. But for the dynamics of that early universe was such that particles survive more than antiparticles. And so we have a universe with particles in it. Typical example of particles and antiparticles are electrons and positrons, which are both emitted in radioactive decay. But when they are emitted, they immediately annihilate into a photon or a gamma ray, which is the E equals C mc squared energy of the two particles, and particle and antiparticles. But it's just for no particular reason, the particles went out. For no particular reason, we have these high resonances in helium. For no particular reason, the amount of mass in the universe and energy was enough at the right balance for the universe to start expanding at the rate it's been expanding. If it expanded any faster, there wouldn't be enough density of material to form stars. If it expanded too much slower, the stars would be so hot that this thing that we're looking at here couldn't happen. So this is what's called, let's say go to the next slide, I think. No, that's what's called the anthropic principle.
Yeah.
And the idea is there must have been a plan behind all of this. It's just too many things that just happen to be just right for the universe not to have been created intentionally. Polkinghorne then goes on to talk about the more of the sort of pregnancy of the universe to work out the creation of life, and then the whole interplay of coincidence and necessity that led to the development of this amazing development of life, which is kind of shown on the right-hand side, going from single cells to photosynthetic creatures to eukaryotes to multicellular, and finally to animal life and human beings. Go to the next slide. So this is his point primarily. The balance between the fundamental forces, gravity and electromagnetism, is what it is and no different. Only because the stars have been able to burn for billions of years that are necessary if they're to have enough to fuel the development of life in a planet, only because the laws of nuclear physics are what they are and no different, has the range of chemical elements necessary for carbon-based life been produced by the stars, whose dead ashes, and we are all children of the stars, and other living creatures here on Earth are made. This remarkable collection of scientific insights into a finely tuned specificity for a biologically generative universe is what is called the anthropic principle. I think is that the end, Dave? No, there's more.
Right. Here's the fun part now.
Oh, yes. Well, okay, that's the good news. Then there's some bad news. There's all sorts of threats to life. Asteroids, huge meteorites, bits of comets are all floating around in the universe and can and have wiped out whole species in the history of the Earth. The dinosaurs being the prime example. Next slide. But we have other threats to our existence. The threat of nuclear war, which Poking Thorne calls human hubris or carelessness. Global pollution, changing the environment warming up. These things also could just about wipe out the human race. Next slide. But those are things which have some probability. There are two catastrophes that are certain. There's no probability associated with them. In about 5 billion years of time, our sun will go through its stellar evolution, its general stellar pattern. It will exhaust the hydrogen in its core, and then it will swell to become a red giant, and the surface of the sun will come very close to the Earth. And everything on the Earth will be fried. The Earth itself may evaporate. That's going to happen. So life on this planet is going to end. Next slide. But that fact weren't big enough. The universe itself is going to end one way or the other. It's either going to expand so much that the protons within the universe will be so far apart that they cannot interact with one another, and all photons will have disappeared. Sounds like C.S. Lewis's Hollow Man poem. This is the way the world ends. This is the way the world ends. This is the way the world ends. Not with a bang, but a whimper. If, however, that's it, only if the energy in the universe keeps it expanding. But there's also a possibility that there's so much dark matter in the universe, and we'll talk about that later, that the universe will actually start to collapse again on itself. And in that case, it'll collapse back almost to a singularity, and it'll just like be a cosmic melting pot. We know this is going to happen. One of these ends must happen. The universe cannot stay a steady state entity. It's got to either expand or contract. And so it will end. But that will be a long time away. Next time. So the realization from science that these catastrophes are going to happen have caused many scientists to be very gloomy, considering that whatever the universe and whatever life is, it's ultimately futile. And that's got to be balanced with looking at the rational beauty and the fruitful history of the universe, showing a divine creator behind it. And why would a divine creator create something that's totally futile? So we Christians have a postmortem, as Polkinghorne uses the phrase, a postmortem hope of the faithfulness of a living God. And so that's the question of theology, is how to balance a realistic approach to the catastrophes with our postmortem hope in the faithfulness of a living God. And I think that's the end of this part of it.
Yep, it is. Okay. So I will go off screen share. Everybody back? Good.
Yes.
Yes.
Wow. Okay, Art, that kind of blew my mind. Do you want to go into the next already, or do you want to have a little discussion?
Why don't we just have a little discussion about what Polkinghorne said in this chapter?
Great. I guess the thing that I was really impressed with, well, I had this feeling when I went out to look at stars on Scudic Point, kind of near where we live in Maine, and it's one of those dark places. So the astronomer showed us everything, and of course, you know, like hearing this, it was just enough to make my mind expand beyond my little perspective. But it was that sense of, my gosh, how big everything is, how vast, just truly awe-inspiring. And I'm curious, what are some of the reactions that you all have had with the reading of Polkinghorne and hearing this presentation on chapter 1? Any questions you've got or thoughts?
I think Art did a great job.
Yeah.
Because in reading this, I'm not scientific. I had a hard time understanding what he was trying to say. And he used tremendously big scientific words. I had to use my iPad and Google a lot to understand exactly what it all meant. And I can't say I still understand, but thank you, Art. It was a great presentation.
Yeah.
But I do have a question. We're in the Milky Way galaxy. There's multiple galaxies. So.
Multiple galaxies? Yes. Those are just clumps of the original hydrogen and helium gas that clump together. When they clump together, that left space between them. So they clumped into galaxies. They clumped into stars. The stars have gravity. They attracted each other. And so they became a group of stars in a balance between gravity and they started rotating, and their centrifugal force as they rotated and their gravity towards each other.
My question is, since we know there's multiple galaxies, there's probably multiple Earths. Are the scientists studying that?
Oh, yes. there's a intensive search for Earth-like planets. Or first of all, there's an intensive search for planets.
Yes.
Kind of interesting the way astronomers can detect a planet. They look at a star somewhere, a very, very high resolution telescope, and they look for a little periodic brightening and dimming of that star, which is caused by a planet passing around the star between the telescope and the star. So if they see stars brighten and dimming, get brighter and dimmer, or mostly dimmer, right? And it's just a little bit of dimness because it's a little tiny planet passing and casting a shadow on a great big star. But they see this, and they've worked out a lot. It's amazing how much astronomers can dig out of a little bit of data.
The question arose because Polkinghorne is really discussing our Earth in this book and our future and what will happen here. But will it be what's the word? Will that happen elsewhere at the same time? I guess.
Will the evolution of the cosmos happen, or?
Well, I mean, if there's multiple Earths possibly out there in other galaxies,
Yeah.
when this collapses here, our futility, will that also happen there at the same time? I'm just curious.
If the
I'm off
universe-
topic, I'm
okay.
sorry.
Yeah, sure. But let's say the universe expands out into nothing and it ends not with a bang but a whimper. The time scale is so many hundreds of billions of years apart since. First of all, the stars will all eventually go through their stellar history and become supernovae, and the density will not be enough for new stars, for gravity of new stars to pull them together. Or the density of the dirt, of the dust of those supernovae will not be high enough for the gravity to pull the dust together and form a new star, which is what happens now.
Okay, so when we come to an end, everything comes to an end.
Everything comes to an
Okay.
end.
All right.
Interesting. Hey, any other questions for Art?
Interesting.
C.S. Lewis explored this idea of there being other creatures in the universe. In fact, he explored the idea of there being other creatures in our own solar system, in Out of the Silent Planet and Paralandra, two of his books.
Great. Well, thank you, Art. And so now I feel like I kind of know why we're considered stardust.
So we are stardust, very
Yeah.
literally.
Yeah, it's interesting to see how carbon-based, how carbon formed to form us. Okay.
Well, it's not only interesting, it's very, very, I mean, to me, it points so strongly to God being behind it.
Yeah. And, Art, I was wondering about that as I was reading the chapter. The three existential questions are, where do we come from? Where are we going? And why are we here? And I remember in taking like biology, chemistry, and physics in high school, it was taught from a very secular perspective, which they had to, which is fine. But as a young teenager, I got the sense that we just came from an accident. And we had current events for our history class one year. And we talked a lot about the nuclear threat and how we had enough armaments to destroy the Earth over and everything in it 14 times. So as a young high schooler, it was like, okay, we came from an accident. We're going into this nuclear frying pan. And the question of, well, why are we here was, for this teenager when I was in that age, was, woohoo, it's time to party. There just wasn't much of a sense. And I'm curious, with you and your own faith development, Did you go through any times where it was your faith, your worldview was really challenged by studying the sciences, physics in particular?
Oh, I guess not. It may be that I just wasn't critical enough. I grew up having a faith in God, and my questions generally were not what sense did this all make? What sense is made of it? My questions generally were, God, what do you want me to do next?
Cool. Yeah. Yeah. Very neat. Okay. Shall we dive into the next chapter? Do we have enough time to hit chapter 2?
Yep,
Okay. Everybody
fired up.
fasten your seatbelts, folks. We're going in.
Yeah,
Let's see if I can get things around here just a second.
this is going to be a high G trip. It's going to,
Yeah.
G, I didn't know that. G, I didn't know that. Okay,
Okay.
so Polkinghorne uses this expression ex vitere. I had to look it up myself, but it's Latin for out of nothing. The Polkinghorne talks about the universe being created not just by God being a divine magician snapping his finger and bringing it all into being, but it was a continuity of creation between old and new. Everything old generated something new. Next slide. He also mentioned general relativity. I'm going to hit some of these things just to talk about it. So this is Einstein's theory of relativity is one of the great intellectual feats of the last 200 years. And it has much to do with things traveling close to the speed of light. It brings up questions about causality. But one of the things is that it has begins to talk about the space-time continuum. So Einstein had this idea, which is hard to think of a four-dimensional space, 3 dimensions of distance and 1 dimension of time, which is hard for the human mind to wrap around because we only see the 3 dimensions of space and experience it. We experience time, but there's no way of seeing it. It's very hard to draw a diagram of a 4-dimensional space. But the little diagram on the right attempts to do that. And Einstein's theory was that mass warps the 4-dimensional space-time continuum. And so he explains gravity by being this warped space-time continuum. For example, the sun, which is huge, makes a big bowl in the space-time continuum. The planets then get trapped in that bowl and just roll around and around in the bowl. And that's gravity. It fits completely with the Newtonian theory. The effects are all the same, but it gives an underlying reason for gravity, and that is a warp in the space-time continuum, which brings up this whole idea of the space-time continuum. Next up. However, the quantum mechanical effects in this thing get to be really weird. And he mentions the EPR effect, which has to do with what's called entanglement. And this is when 2 particles are to come together, like 2 protons in a nucleus. If they become entangled. It's a quantum mechanical phenomenon. And basically it means that no matter how far these parts get separated in the future, if what some aspect, like the one that's used most of all is the spin of the particle. Our particles have a inherent quantum mechanical spin. And it can be, it's all relative to some directions. So two particles can have a spin up and down, one particle up, one particle down, so that when they're together, the total spin of the system is 0. Or they can have two particles that have both have a spin up, and then the total spin of the system is 2. But no matter if they become separated, no matter how far apart they're separated, if you change the spin direction of one of the particles, the spin direction of the other particle will also change to maintain the balance they originally had. And it's a very strange effect, and it's predicted by general relativity. But Einstein couldn't believe it. He said it's spooky action at a distance. So Polkinghorne's point in talking about this is that there are things in our understanding of the quantum mechanical nature that are still mysterious, and this effect has never really been explained by anything even deeper. But there are deeper things someplace. There are deeper things in the universe that we haven't been able to probe down into. Next slide. That's one of them. Now I want to talk about dark matter for a little bit, and I hope I'm going to talk a fair about it, but I think it's just interesting. But it also kind of shows how some of these things come to be understood. Okay, as we have said, originally the universe was made up of gases. The gases clumped together to become stars. Stars began to rotate around in a disk that was a galaxy. And the disks then, kind of over on the right, the disks settle down into a steady state orbits that have lasted for millions and millions of years. Astronomers have studied the spin of galaxies, especially disk-like galaxies. And they wanted to understand how the physics worked in it. Next slide. So it's very simple using the laws of gravity and everything. Distribution of mass, angular momentum, to predict the orbits of things in a spinning disk like this, where there's a balance between gravity and centrifugal force. And so the little curve on the right, labeled ABCD, is a curve showing the orbital speed of something at A as a function of its distance A from the center. So you see this curve is going down. So mass closer to the center of a galaxy is going to move faster than mass out towards the edge of the galaxy. And that's predicted from the basic physics of gravity. So let's say, I think the next slide. So what astronomers did is they've looked at galaxies and they've used a feature of the electromagnetic spectrum which is called the red shift or the blue shift. And it's like since light is a vibration, it's like sound. As a train comes towards you and that passes by you, the pitch of the horn of the train changes. And so actually the frequency of the light changes as it's either coming towards you or going away from you. So astronomers look at their telescopes are good enough so that they can measure the light spectrum across the galaxy itself. And for our galaxies that are millions of light years away, that requires an extraordinarily high resolution and the spectrometers that can work with very little light. But basically, if they look at the diagram, you see stars out at A in the galaxies are going to be blue shifted because the light's coming towards you. Stars out at C are going to be red shifted because the stars are going away from you. And the amount of that shift they can calculate the actual velocity of the stars in that region of the galaxy. So now they know now they can plot the galaxy regional velocities as a function of distance from the center of the galaxy. Now, the previous slide, we showed how that changed. And go to the next slide. And here's what's absolutely blew everybody's mind, talking about having your mind blown. The red curve is what's predicted from the, they can also tell the mass from how bright the light is. So now they've got the mass and they've got its velocity. And so they can put regions of that galaxy on this curve where it should be, which is the red line. Whoa, what they saw, the data they collected was actually the blue line. Totally different. And they found out, I mean, this happened in galaxy after galaxy after galaxy after galaxy. It's something about galaxies out there. And there's a lot of galaxies out there to look at. But they said, what in the world could possibly cause this? The only thing they could think of is that there's mass there that they weren't seeing. And they explored all sorts of different things for what this mass could be, but there was just absolutely nothing that showed up as being something that they could detect there. So they called it dark matter. And the current theory is the universe is full of a kind of matter that gives off no light, but it has gravitational attraction.
Is that the same as black holes then, Art?
No, that's not the same as black holes.
Oh, okay.
Dark matter is spread out all over the place. It's not necessarily clumped together in one place.
Okay.
What they've it's amazing what astronomers can tease out of their observations, but they've concluded that the galaxies are all surrounded by a halo of dark matter. Now, our galaxy is surrounded by a halo of dark matter. We're just in a big, it's like, who's the peanut character? Pigpen. We're just have this dust of dark matter around us as we're going through space. So that's what dark matter is. And that's where it came from. Okay, let's go on. Okay, Polkinghorne also talks about chaos theory. So chaos theory is a study of very complex systems and or chaos study, chaos science, the study of very, very, very complex systems that are sensitive to the finest details of their circumstances. And Polkinghorne gives, as well, somebody gives, I don't think it's Polkinghorne, an example of a weather system. So the little figure on the right is highly diagrammatic, but the horizontal axis is time. And so you have two weather systems, systems blue and systems red. They both start off with about the same initial conditions, but slightly different ones. And over time, those slight differences cause the two systems to become more and more and more different in time. And it can also cause systems to begin to become coordinated in time. It's a very, very strange thing. Some phenomena that are really not very well explained, but they're just spontaneous coordinations in complex systems. And Polkinghorne's point, I think, is that we don't understand complex systems well enough. The next slide. And Polkinghorne also talks about the strange thing about how well mathematics display can be used to explain the natural universe, or to explore the universe. And I'm going to give it as an example, and this is why I haven't gone into using any mathematics in this. That equation in the white box is the exact solution of the fundamental quantum mechanics for a hydrogen atom. One electron orbiting one proton. And the figure is a plot of the mathematics, which is used to plot the probability density. The probability density is the probability that an electron in that orbit will be at that location. And so these go in sort of increasing energy from left to right. At the lowest probability, the electron is probability density is just a sphere around the proton. And then it breaks down into a donut. But then as the thing spins, it becomes more complex donuts as you go down the slide. And then as you go to, there's higher energy states where there's a high probability towards the center, but a low probability that there's another sphere outside the center sphere, and so forth. There are all these patterns, and they're absolutely amazing and beautiful in their own right. But most of all, they correspond to chemistry. They match up with the chemical effects precisely. So this working out of mathematics is able to predict a lot of features in the universe, and that's the mystery. Why is mathematics such a wonderful tool for exploring and investigating reality around us? Is there another slide? Let's see.
Yeah.
Oh yeah. This is the fun one. Okay. This is about the quantum electromagnetic gap. So the little figure is highly schematic, but it shows possible quantum states in a vacuum. So a photon can have a quantum state E0, E1, E2, E3, 4, or 5. They have to jump from one state to another in quantum mechanics because they're quantum. But there's a gap between E0 and 0. It's called the vacuum energy gap. It's absolute nothingness. It's as close as you can get to having nothing. And it's called quantum energy, the vacuum energy gap. But it's in this vacuum energy gap. Remember the virtual particles we talked about earlier?
Yeah.
They show up in the vacuum energy gap. They pop into existence long enough to create a force field, and then they go away. But there are actually some particles that have mass that show up that way too, very briefly, and then disappear. And we're getting into some of the very, very high energy physics stuff then. So go to the next slide then. What has been postulated is that not only there's a fundamental idea of quantum mechanics is that anything that can possibly happen will happen, but with maybe a very, very low probability. One of the examples that are given in graduate quantum mechanics classes is you can set a salt shaker down on the table and it'll fall through the table and show up underneath it. Now the probability of that is very, very, very low, but it is possible that all the atoms in the salt shaker can line up with all the atoms in the table, and the salt shaker will fall right through the table. It's possible, but it's a very, very low possibility.
Yeah.
But there is a possibility that in this low energy gap, a whole universe will bubble up. In that gap will become a collection of particles that contain all the energy and all the mass of the universe. And that may self-annihilate immediately and disappear. But there's a thing in cosmology called inflation. In the beginning of our universe, the universe was expanding, and all of a sudden, within a few minutes of or maybe it's seconds of the beginning of the universe, there was this sudden expansion of the universe. And it's not understood. The physics of the expansion is not understood. But the application is that somewhere in that quantum gap, a whole universe appeared, and inflation caught it and expanded into the universe that we're in. And that's the explanation for the beginning of the universe. It's based in quantum electrodynamics of the four-dimensional space-time continuum and cosmological events.
Wow. Very cool.
I think is there anything else there?
That is the end.
That's the end. Okay.
Oh, Art, that was just amazing. Again, a little bit scary seeing the universe through your eyes, Art, but
well, a lot of that last stuff is speculation, and Pokinsar says it is speculation.
Yeah.
It's just things that people have speculated that might possibly be real.
Yeah. Well, and given in the early part, your first chapter, you talked about just the ideal settings and temperatures for things to happen, and that seems to fit in with that last part, that anything could happen. I mean, if we're here, anything could happen. Well, we are a bit after our 1:30, but thanks so much, Art. Now,
Oh, I'm sorry. I ran
oh,
over.
that's fine. And I do want to just close us with a few words from Psalm 8. When I consider your heavens, the work of your fingers, the moon and the stars you have set in their courses, what is man that you should be mindful of him, the son of man that you should seek him out? You have made him but little lower than the angels. You adorn him with glory and honor. You give him mastery over the works of your hands. You put all things under his feet. And just hearing how physicists have explored this universe and able to harness some of the energy and the secrets, just amazing to me. But it shifts the view of who we are and who God is. Just quite amazing. And then to think that this God shows up to us in Jesus and then in the Holy Spirit and loves us so much. It's kind of mind-boggling that God would love us that much when God's done all this amazing stuff. He's in charge of all these things over these billions and billions of years. Just amazing. Okay, so next week we're going to tackle 3 and 4. Do you all want to still do 3 and 4? You want to just do one chapter at a time? Go for it. Try one more time. 2 chapters. Okay. Well, thanks again, Art. And Art's going to lead us out on those 2 chapters too, because they have the science basis to it. And so we'll look forward to that, Art.
I don't know. I do. That's a challenge.
Is it a challenge? Well, we can talk later and see if you just want to do one chapter and I can do another.
No. If I have to do one, I can do 2.
Might as well do 2. Yeah. That's the spirit. Okay. Well, you all have a great week and see you next week. Bye, Iris. See you.
Hi, everybody.
Bye.
Bye-bye.
Bye-bye.
Thanks, Art.
You're welcome.